Let's talk about Gödel's First Incompleteness Theorem. We're talking through the fundamental limitations of formal systems. So the proof outline that we will follow is that we will consider any formal system that is consistent, it's effectively axiomatized, and it's expressive enough for some arithmetic operations. And what we will do is we will allow F to talk about its own statements using arithmetic. And then what Godel does is he constructs a statement, G, that effectively but not directly says, that G is not provable in F. When we look at that statement, it often reminds people of Liar's paradox. And Gödel's work is often mistakenly conflated with Liar's paradox, which says that this statement is false. And why it's a paradox? Because if that statement is false, then it's true that it's false. And if it's true, then it's false. So it can neither be true nor be false. And that's why it's a paradox. However, Godel does not talk using self-referencing sentences in English. He's not talking through philosophy here. Rather, he's talking about a formal system. And when we talk about formal systems, we're talking about formal systems such as piano arithmetic. Piano arithmetic is formulated in first-order logic with equality using the language, which consists of the constant 0, the successor function, which means, for example, the successor of 3 is 4, the plus and multiplication as binary functions, and the variables range over all natural numbers. Now, piano arithmetic is named after Giuseppe Peano, who was an Italian mathematician and logician, and one of the first mathematicians to insist that mathematics should be built on explicit axioms that you take for granted and then written in a formal symbolic language. And piano arithmetic is quite powerful, starting with the very basic assumptions on the successor function, axioms such as x plus s of y is equal to successor of x plus y, and that 0 is not a successor of any natural number. You can actually prove quite a few different theorems, such as the associative property, the commutative property, none of which are assumed, rather they are proven, so they are theorems, not axioms. The distributive property, more complex theorems such as infiniteness of primes, the pigeonhole principle, the unique characterization of numbers in terms of primes, the correctness of finite state machines and encodings, Ramsey theorem. Quite a few different theorems you can derive in piano arithmetic, starting with those very basic assumptions. And what Godel does is, Godel comes up with the numbering. We refer to it as Godel numbering. That's total, that's injective. So that means it's 1 to 1. And it's a computable function and assigns a unique natural number to each symbol, each finite string of symbols, and each finite sequence of formulas that's proofs. And such as we can say that the Godel number of x is equal to 1, and we use the ceiling looking function to represent that particular notation. When we say that x is provable inside F, we mean that there exists y, which is the proof of x in F. And here's the punchline. What Godel does is effectively constructs this formula, which says that G is equivalent to not provable inside F, the integer, the Godel numbering of G. So G is a purely arithmetic statement inside F. The coding of this formula string that you see here on the screen is the integer, again the Godel numbering of that. So more precisely, consider these symbols that you've written here. G equivalent to not provable inside F, the parentheses, numerals, etc. That's the string using the same Godel numbering. And once you get that coded as a natural number, that is effectively the Godel numbering of G, which is written in the formula. And why does G break completeness? Well, if F proves G, then F proves a false statement, therefore the system wouldn't even be consistent. Now, if F proves not of G, then F proves that a true statement is false. That's also inconsistent. So therefore, to avoid either contradiction, if F is consistent, then G is true, but it's not provable inside F, and hence F is incomplete. And this is also the good time for us to remember what's a consistent system versus complete system. Consistent system is something that simply says that there are no contradictions, which means you're not able to prove any false statement. A complete system, on the other hand, says that you're able to prove every true statement. If a statement is true, then it can be proven in that particular system. What Godel has just come up with is that no sufficiently strong formal system can be both complete and consistent, and therefore that the truth strictly exceeds provability. There are limits that are intrinsic to formal reasoning, not because we cannot come up with that, just because they are intrinsic to the formal reasoning. Now, Godel does assume that the system has to be sufficiently strong for us to be able to do encodings such as the Godel number itself. So that's Godel's first incompleteness theorem for you, and it's quite insightful.